In this video, we're going to be looking at some key terminology for sequences, as well as an important theorem telling us how these properties relate to when a sequence must converge. So our first couple of terms have to do with when sequences are increasing and decreasing. So we say that a sequence AN is increasing if you have AN plus 1 bigger than AN, so the next term of the sequence always bigger than the previous term for all n greater than or equal to 1. So an example of an increasing sequence would be something like 1, 2, 4, 8, 16 here. So our sequence is growing in size with each term. We're going to also have a definition called non-decreasing. This just means you can have your sequence stay constant on the next term, so not strictly increasing. So this would be for AN plus 1 bigger than or equal to AN. So this sequence, this example of a non-decreasing sequence might look like 1, 1, 2, 2, 3, 3, for example. So the next term is either bigger than or equal to the previous term. Our sequence is decreasing if it's the fact that the next term of the sequence is always smaller than the previous term. So you could have something like 1/5, 1/7, 1/9, etc. So the next term here is strictly smaller than the previous term. We can also have a non-increasing sequence where we just have the next term is either equal to or smaller than the previous term. So you could have something like 0, -1, -1, -2, -2. So the next term in the sequence is either smaller than the previous term or equal to the previous term. Okay, so just being familiar with these definitions will be helpful as we make use of some of these properties in later theorems that we're going to learn to do with series convergence in particular. So just a few more definitions associated with our sequences. So we say that a sequence is monotonic if it's either non-increasing or non-decreasing. So this monotonic here, mono meaning one, tonic meaning direction. So it moves in one direction. So when we say either non-increasing or non-decreasing, this includes the cases of increasing and decreasing. Okay, so it just has to either be moving in an upward direction, maybe it's allowed to stay constant, or moving in a downward direction, possibly staying constant. Those will all be cases of monotonic sequences. Okay, so we're going to see a little bit later that monotonic is a nice property for a sequence to have that allows us to conclude some various things about how that sequence behaves. So other key definition that we're going to need from time to time is whether a sequence is bounded. So we say that a sequence is bounded above if there is a number big M so that the terms of our sequence are always less than or equal to that number. Okay, we'll say for all n, or for all n big enough in the sequence. So an example of a sequence that's bounded above, you could have the sequence 1 minus 1 over 10 to the n, where this sequence would be 9/10, 99 over 100, 999 over 1,000, etc. So the terms here are all bounded by 1. Okay, we will say that a sequence is bounded below if there is some number, let's call it n, so that the terms of our sequence are always bigger than that number n. Okay, so for example, if I had a sequence 1, 2, 3, etc., just my sequence of integers, these terms are certainly always bigger than 0, so the sequence in this case here is bounded below, let's see, up here it was bounded above by 1. This example here, I have a sequence that's bounded below by 0, for example. Okay. If a sequence is bounded both above and below, we say that the sequence is a bounded sequence. So that's a nice property for a sequence to have. So just for an example here, if I had the sequence 1 over 2n plus 3, okay, the terms of this sequence look like 1/5, 1/7, 1/9, etc. Okay, so we see that this particular sequence will be always positive, so it's certainly bounded below by 0, and it will be less than or equal to 1/5. So we're looking at the terms here. The terms are getting smaller as we go on. The next term is smaller than the previous term. So that first term would actually be the maximum value for that particular sequence. So that's an example of a bounded sequence. In pictures, we think of a bounded sequence here as staying between some numbers m and some number n. So the sequence might oscillate, it might increase, but it has to stay between these two values. So it can't get too big and it can't get too small if it's a bounded sequence. So let's look at one example where we practice applying these different terms here. So let's determine whether the following sequence, which is given by -2 to the n plus 1, converges or diverges, and then state whether it's monotonic or whether it oscillates. Okay. We'll also look at whether this sequence is bounded or not. So notice here, let's say that my index here starts at 0. So this is for n equals 0, 1, 2, 3, etc. We'll notice that on a lot of sequence problems, we're not given what the starting index is, because usually we're just interested in what happens as n goes to infinity, so it doesn't matter where n starts. But if I wanted to write out the initial values of this particular sequence, I'd need to know where it started. So let's say it starts at 0. So if I plug in 0, the first term here would be -2. If I plug in 1, I would have -2 squared, so that's 4. Then I would have -8, then 16, -32, etc. Okay. So we can see that this particular sequence is not going to be monotonic. I'm going to have -2, and then I have, let's see, I have 4, and then I'm going to have -8, and then 16, and then -32 is going to be way off the page here, but it's going back and forth, it's actually oscillating. So we would say, therefore, that is not a monotonic sequence. Okay. So we gave some examples earlier of some monotonic sequences. This one is not monotonic. This one is also not bounded. It's actually not bounded above or below in this particular case, since I have some terms that are going off to -infinity and some terms that are going off to infinity. Okay. It also turns out that this particular sequence diverges. Okay, we see it's oscillating back and forth. It's not going to one finite number, so that's an example of a divergent sequence. Next, we're going to see how these ideas of being bounded and being monotonic are connected to a really important theorem about sequence convergence. So we have something called the Monotonic Sequence Theorem, which states that every bounded monotonic sequence is convergent. Okay, so what does this mean? Let me write that out in a little more detail. This says if a sequence is bounded, meaning bounded above and below, okay, and it is either increasing or decreasing, it must converge. That's what this statement is saying. Okay.
So if you have the properties of being bounded and monotonic, bounded being staying within some strip and either being increasing or decreasing, the sequence must converge. So let's just draw a picture and think about why that is. So if you're, let me draw some bounds here. Let's say I have to stay between those two red lines and my sequence is increasing. Okay, well then it has to be converging to some value. It can't exceed this upper bound here, and it's always getting bigger than the previous value, so it must converge to something. Similarly, if I have my sequence having to stay between two bounds and being decreasing, oops, let me use my other color here, then again that sequence has to converge. Okay.
Now let's look at these two conditions in a little bit more detail for this theorem. So we know that the theorem says that if a sequence is bounded and monotonic, then it must converge. So is it possible to converge and not have these conditions? Let's just look at this a little bit more closely. So our first note is to say that it is possible to converge without being monotonic. And we've seen this sort of situation before. Oops. Without being monotonic here. Okay, because we can have something that oscillates, but the oscillations just get smaller over time. So we can have something that sort of goes up and comes down, but then those oscillations start to get smaller, and it is actually converging to something. So it's possible to converge without being monotonic. So what about the bounded condition? Is it possible to converge without being bounded? And the answer is no. So it is not possible to converge without being bounded. But being bounded alone isn't enough to show convergence. So it's not possible to converge without being bounded. Okay. But if all you know is that something is bounded, that doesn't tell you that it converges. So, but the bounded condition alone does not imply convergence, because we could have something that's oscillating and the oscillations aren't getting any smaller over time, and so it just bounces back and forth between two values. So this was our example up here. Down here, it's possible for me to have something that is bounded, but it just keeps oscillating. Okay. So we've got an idea of some of these different scenarios. We know if something converges, it does have to be bounded. If something is not monotonic, it might converge if it's the right sort of monotonic, even though bounded wasn't required there. But overall, what we now know from this theorem is if a sequence is bounded and monotonic, it must converge. Okay, and that concludes this section on sequences.